You stand quietly on the observation deck, feeling the subtle vibrations from the immense Saturn V rocket below. Its height stretches over 360 feet, and every detail has been meticulously designed to convert stored chemical energy into enough force to escape Earth's gravity. Engineers move systematically, performing final inspections of the engines, the guidance systems, and the complex plumbing that delivers liquid hydrogen and oxygen to the combustion chambers. You notice the careful measurement of each valve and conduit, understanding that even a minor misalignment could affect the launch trajectory. The countdown is not merely a dramatic formality. It represents the precise synchronization of hundreds of systems, each dependent on exact timing and scientific calculations. Fueling begins with the slow introduction of cryogenic propellants. Liquid hydrogen, chilled to -253 degrees Celsius, flows with careful monitoring. Liquid oxygen, brighter in its reflective sheen, moves through its own conduits. You follow the instruments that track temperature, pressure, and flow rates, observing how sensors continuously report values to ensure that both fuel and oxidizer remain within safe limits. The process is gradual and deliberate, with no rush, as any sudden change could create dangerous conditions. Every parameter is checked against expected tolerances, illustrating the engineering principle that safety in space relies on exact replication of expected conditions. You watch the crew in their white launch suits, moving methodically through pre-flight routines. They enter the command module, seated in carefully measured positions that optimize both comfort and accessibility to controls. Their suits contain integrated life support systems, providing oxygen, temperature regulation, and communications. You note how even body orientation, seat cushioning, and restraint straps are designed to minimize stress during launch, distributing forces according to human tolerance limits. Engineers confirm the proper operation of the environmental controls and the interface between the astronaut suits and the spacecraft systems. You absorb the methodical discipline, understanding that each action is rooted in extensive research and prior simulations. As the countdown reaches T-10 minutes, a sequence of checks begins. The guidance computer is powered up, running pre-flight diagnostic routines. You follow how gyroscopes and accelerometers are calibrated to detect any deviation in orientation. Telemetry systems link the rocket to control centers, allowing real-time observation of pressure, temperature, vibration, and electrical load. Every cable, sensor, and signal has been verified multiple times over. The engineers' calm voices over the intercom are precise and measured, their instructions clearly tied to maintaining physical conditions within calculated margins. The synchronization of human judgment and automated monitoring exemplifies applied physics in motion. The main engines ignite first, producing over 7 million pounds of thrust. You feel the ground tremble as combustion transforms chemical energy into kinetic energy. The rocket begins its slow lift, accelerating upward in a carefully calculated curve to achieve the correct trajectory for orbit. You notice how the gimbaled engines adjust in real time to maintain alignment with the flight plan, counteracting even minor deviations. Aerodynamic forces act on the rocket, yet the shape and structural reinforcement have been optimized to reduce drag while withstanding immense mechanical stress. You track the gradual increase in velocity, the delicate balance between acceleration and the structural integrity of the vehicle. Stage separation occurs smoothly. The first stage, now depleted, is released, and its engines fall away into the ocean. You follow the calculations that ensure the upper stages ignite precisely when needed, maintaining the spacecraft on a trajectory that accounts for gravitational pull, atmospheric drag, and rotational motion of the Earth. Every fraction of a second is governed by Newton's laws and the conservation of momentum, demonstrating the direct application of physics in guiding the rocket. Your mind lingers on the way small adjustments in fuel flow or engine angle translate into large changes in orbital parameters, a reminder of the sensitivity of motion in space. You notice the transition to the second stage, engines firing to continue the climb. Telemetry shows increasing altitude and velocity, steadily approaching the boundary of space. Engineers on the ground monitor vibration frequencies, fuel depletion, and guidance alignment. Each signal confirms that the sequence is proceeding within calculated tolerances. The command module remains protected within the third stage's fairing until the proper altitude is reached. You track the temperature of the cabin, the status of life support systems, and the communication signals, all within expected ranges. Every measurement reassures you of the reliability built into both human and mechanical components. The final stage ignites, providing the final push toward translunar trajectory. You observe how trajectory calculations integrate gravitational influences from both Earth and the Moon. Small course corrections are planned and executed through controlled engine burns. You follow how engineers and astronauts anticipate even minute perturbations, such as solar radiation pressure or irregularities in Earth's gravity field. The spacecraft's speed increases, gradually escaping Earth's dominant gravitational pull. You notice how orbital mechanics, grounded in centuries of observation and Newtonian analysis, guide the motion of the spacecraft through a vast, empty sky. Within minutes, the command module separates from the spent third stage. The spacecraft is now fully powered by its own guidance systems and onboard fuel. You track the stabilization maneuvers, ensuring that rotational momentum and center of mass align with the intended flight path. Instruments measure angular velocity, thruster efficiency, and thermal conditions. Every system is operating within its expected range, a testament to rigorous pre-flight modeling and repeated simulation. You feel the calm orderliness of human understanding applied to the seemingly chaotic environment of space. The crew reports all systems nominal, and you notice the subtle rhythm of human activity inside the capsule. Instruments are monitored, checklists are followed, and communication with mission control remains steady. The combination of careful preparation, precise calculation, and continual observation maintains a controlled environment, ensuring that every element functions in harmony. You reflect on how each action, though invisible from Earth, represents the culmination of decades of aerospace research, material science, and applied mathematics. As the spacecraft continues to climb, your mind traces the immense energy required to lift it beyond the atmosphere. The mass of the rocket, multiplied by the acceleration needed to overcome gravity, translates into millions of joules of work. You observe how chemical energy converts efficiently into motion, and how every stage is engineered to maximize the ratio of thrust to weight. Even small inefficiencies are significant at this scale, yet each system operates with the precision of well-tested science. You feel a quiet awe for the predictable, measurable forces that propel humans beyond Earth's surface. The spacecraft passes the Kármán line, entering the thin upper layers of the atmosphere. You notice the decrease in atmospheric drag, the change in acceleration, and the transition from the thick, turbulent lower air to the near vacuum of space. Temperature gradients are monitored, and instruments report normal readings. You sense the quiet calm of a controlled environment outside the turbulent Earth. Every reading confirms the effectiveness of engineering, physics, and careful planning in guiding the rocket safely through the last critical layers of the atmosphere. You watch as the engines cut off, leaving the spacecraft in a stable orbit. Microgravity begins to affect the crew, and you notice how motion and mass now behave differently in the absence of dominant gravitational force. The spacecraft coasts, its momentum carrying it forward with calculated precision. You reflect on the convergence of scientific understanding, human skill, and careful preparation that has made this moment possible. Each system operates predictably, and the crew remains safe within an environment engineered to maintain life while they orbit high above the Earth. Your mind lingers on the quiet coordination required to achieve orbit. The balance of forces, careful monitoring, and precise timing demonstrate the predictable nature of physics, even in extreme environments. You consider the next calculations that will guide the spacecraft further, where celestial mechanics and human ingenuity continue to intersect. The journey has begun with exactitude, and the interplay of energy, mass, and motion quietly promises the challenges and discoveries that await beyond the edge of our planet. You feel the gentle vibration of the spacecraft as it stabilizes in low Earth orbit. The engines have cut off, and momentum carries the vehicle along a curved path around the planet. Outside, the Earth curves beneath you, and its atmosphere thins gradually into the blackness of space. You notice how orbital velocity balances gravitational pull, a precise equilibrium described by Newton's laws. Every calculation that brought the spacecraft here ensures that it neither falls back to Earth nor escapes too early into interplanetary space. The understanding of centripetal force, velocity, and mass allows this delicate balance to persist, keeping the crew in a stable orbit as they prepare for the translunar injection. You observe the crew checking instruments and systems. Electrical systems display voltage readings, fuel cells indicate energy reserves, and life support sensors monitor oxygen, carbon dioxide, and cabin pressure. The astronauts' routines are calm, methodical, and repetitive, designed to maintain the integrity of the spacecraft and their own physiological needs. You notice the integration of human observation with automated systems, each complementing the other. Data from sensors is continuously analyzed against expected ranges, and any deviation prompts a carefully calculated adjustment. You see that even in the quiet of space, the application of physics and engineering remains constant and precise. The mission trajectory is calculated to exploit Earth's gravity while gradually accelerating toward the Moon. You watch the spacecraft execute a translunar injection burn, its engines firing for several minutes with carefully measured thrust. Calculations take into account the spacecraft's mass, the changing gravitational pull of Earth, and the target path toward the Moon. You notice that the timing and duration of this burn are critical. Even a small deviation in speed or angle could alter the course significantly, potentially requiring additional corrections. The mechanics of motion through space, free from air resistance, reveal the predictive power of classical physics when applied with precision. You notice the spacecraft beginning to accelerate away from Earth's orbit, the increasing distance gradually weakening Earth's gravitational influence. You track the velocities reported by onboard instruments, measured relative to the planet and to the Moon. The crew monitors course stability and fuel usage, understanding that excess consumption may limit future maneuvers. Every thruster firing is carefully computed to conserve fuel while ensuring that velocity changes align with predicted orbital mechanics. You feel the steady, controlled precision of human planning applied to an environment where small forces have lasting consequences. As the spacecraft moves farther from Earth, you observe how solar radiation and micrometeoroid flux become relevant to navigation and safety. Instruments monitor radiation levels, and trajectory calculations consider the minimal but measurable effects of solar pressure on the spacecraft. The crew adjusts shield orientation and checks the structural integrity of panels exposed to the near-vacuum environment. You notice the care taken to maintain stability and prevent gradual drift from the planned path. Even imperceptible influences require attention, illustrating how detailed scientific observation guides every moment of the mission. You watch the crew as they continue monitoring the spacecraft systems. Water, oxygen, and electrical power are tracked closely. You notice how energy conservation becomes critical during extended periods of propulsion and coasting. Electrical systems convert stored chemical energy into operational power with predictable efficiency. Environmental control systems maintain stable temperatures within the command module, using heaters and radiators controlled by thermodynamic calculations. Even the subtle effects of heat transfer in microgravity are considered, with engineers designing each system to manage thermal equilibrium carefully. You sense the continuous presence of applied physics, quietly maintaining life and function. The spacecraft passes the halfway point between Earth and Moon. You observe how the balance of gravitational forces begins to shift. Earth's pull weakens while the Moon's gravity gradually becomes more influential. You notice how mission planners account for this gravitational transition to refine the trajectory, ensuring that the spacecraft arrives near the desired lunar approach corridor. Calculations involve mass ratios, velocity vectors, and timing of minor course corrections. You understand that even in near-empty space, the interplay of celestial bodies follows precise, predictable laws, and navigation relies on detailed understanding of those laws. You observe the crew performing routine maintenance and scientific observations. Experiments designed to measure microgravity effects, radiation, and orbital mechanics are conducted carefully. Sensors record data about cosmic rays, solar wind particles, and temperature variations. You notice how the spacecraft's instruments provide continuous streams of information to both onboard and ground-based analysts. Each observation reinforces understanding of environmental conditions in space, allowing scientists to compare real-time measurements with theoretical predictions. The consistency between observation and calculation underscores the reliability of applied science in guiding human exploration. You notice the subtle course corrections executed using reaction control thrusters. These thrusters apply very small amounts of force to adjust orientation and velocity. Calculations take into account Newton's third law. Every action produces an equal and opposite reaction. The crew measures each firing carefully, noting changes in angular velocity and translational speed. You follow how even a brief thruster burn can gradually refine the trajectory, and how accumulated small adjustments maintain the spacecraft on a safe and predictable path toward the moon. This continuous application of physics ensures that despite distance and time, the spacecraft remains precisely where it needs to be. You observe Earth slowly shrinking behind the spacecraft, its blue and white swirls growing smaller. You follow the calculations that account for rotational motion, orbital inclination, and velocity relative to the moon. The crew verifies communication systems, ensuring that telemetry remains accurate across increasing distances. Signal travel time is calculated, as radio waves take over 1 second per 300,000 kilometers to move from the spacecraft to ground stations. You note how physics governs not only the motion of massive bodies but also the transmission of information across space. Every calculation, every correction, relies on laws that have been verified over centuries. The moon grows steadily larger ahead. You observe how navigational instruments prepare for approach, measuring distance, relative velocity, and trajectory angles. Orbital insertion requires precise calculation of braking maneuvers to reduce speed relative to the moon. The crew monitors fuel reserves to ensure that planned corrections remain possible. You follow how the combination of mathematics, observation, and engineering allows the spacecraft to arrive within kilometers of the intended orbit. Gravity becomes a tool as well as a constraint, with careful application ensuring that the spacecraft can safely enter lunar orbit or conduct maneuvers without overshooting. Throughout the journey, microgravity affects crew routines and scientific measurements. You notice how daily life adapts to weightlessness with careful monitoring of fluid movement, food intake, and muscle activity. The life support systems operate with precision, managing oxygen, pressure, and temperature. You observe how physiological responses are considered in mission planning and how systems are designed to maintain equilibrium. Even routine actions like moving within the spacecraft are guided by an understanding of inertia, momentum, and Newtonian physics. Your mind tracks the seamless integration of human activity, mechanical systems, and orbital mechanics. Each calculation, observation, and adjustment demonstrates the predictability of physical laws when applied with care. The spacecraft moves steadily toward its target, guided by calculations, sensors, and the subtle inputs of the crew. You sense the elegance of the system, where energy, momentum, and gravity interact in predictable ways, allowing humans to traverse hundreds of thousands of kilometers with confidence. You feel the quiet anticipation as the moon approaches, its gravitational influence growing more noticeable. Calculations predict the precise moment when maneuvers must adjust speed and angle to ensure safe arrival. You recognize how understanding gravity, motion, and momentum allows controlled navigation across space. The journey itself is a demonstration of applied physics, engineering, and careful observation, showing how human knowledge can guide travel across vast distances. The spacecraft glides silently, steadily, and predictably, poised to encounter a new celestial environment shaped by the laws of nature. You feel the steady hum of instruments inside the spacecraft as the crew continues routine monitoring. Telemetry streams display oxygen levels, electrical currents, and pressures within the various tanks. Each reading is compared against expected parameters, a constant process that integrates human observation and automated systems. The command module's environmental control monitors oxygen flow into the cabin, tracking consumption rates based on crew respiration and the operation of life support systems. You notice the fine balance between stored resources and usage, and how precise engineering predicts how long each tank will sustain the crew under normal conditions. Suddenly, a sharp spike appears on the pressure gauge of the number 2 oxygen tank. You follow the data as the system records a rapid decrease in oxygen quantity, accompanied by fluctuations in voltage from the fuel cells. The spacecraft's telemetry reflects the interplay of chemistry and electricity, as the fuel cells rely on oxygen to generate electrical power. A failure in the tank affects not only breathable air but also the electrical systems critical for communications, guidance, and temperature regulation. You observe how a single component's malfunction cascades through interconnected systems, illustrating the sensitivity of spacecraft design. The technical cause is traced to a combination of factors within the tank. You examine the wiring insulation that had degraded over time, a condition exacerbated by storage at cryogenic temperatures. When the heater switch had been used during ground testing, it had exposed the thin Teflon insulation to high temperatures, causing unnoticed damage. You follow the physical and chemical processes at play: insulation breakdown, electric arcing, and the sudden release of stored energy within a pressurized vessel. The physics of gases, including expansion under heat and the mechanical limits of the tank walls, explain why the rupture was both sudden and forceful. You notice how engineers analyzed the tank's behavior in detail after the event. Thermodynamic calculations indicate that the tank's oxygen, initially at low temperature, rapidly expanded when heated beyond its design limit. The increase in pressure exceeded the structural strength of the tank, leading to a violent explosion. Material properties of the stainless steel tank, including tensile strength, ductility, and weld integrity, determine the point at which rupture occurs. You observe that this failure is predictable when stress, temperature, and material limits are considered, illustrating the importance of engineering safety margins. The spacecraft responds immediately to the event. You follow the electrical and mechanical consequences as power drops, alarms trigger, and systems respond to abnormal conditions. Fuel cell output diminishes, leaving only backup batteries to maintain life support and essential communications. You notice how redundancy is a core principle of spacecraft design, with multiple independent systems capable of sustaining operations temporarily. The crew quickly evaluates the situation, relying on both their training and real-time data from the instruments. You sense the calm application of scientific reasoning under pressure. You watch the oxygen levels in the command module decrease gradually, illustrating the effects of limited resources. Carbon dioxide begins to accumulate, and the environmental control system adjusts flow rates to maintain breathable air. You follow the chemical reactions involved in oxygen generation and removal of carbon dioxide through lithium hydroxide canisters. The efficiency of these reactions is critical. The crew calculates how long current reserves can sustain them. You notice how applied chemistry and physics intersect with human physiology, ensuring that life support decisions are guided by predictable, measurable principles. The crew coordinates with mission control to analyze telemetry and determine next steps. You follow the logic used in calculating resource availability. Electrical power, oxygen reserves, and water supply are continuously quantified, integrating data from multiple sensors. The interplay of physics and mathematics determines permissible activities, power usage, and potential course corrections. You observe how every action is constrained by measurable parameters, and how engineering and operational discipline converge to maintain safety. You notice the spacecraft systems designed to isolate damaged components. Valves are closed, circuits disconnected, and flow redirected to minimize further loss. The careful application of fluid dynamics and electrical engineering ensures that damage is contained. You follow the physics of pressurized systems, noting how isolating a compromised tank prevents cascading failures in connected plumbing. The crew monitors pressures and flows, confirming that interventions stabilize the situation, even as overall capacity remains reduced. Attention turns to the potential for additional failures. You observe engineers calculating remaining oxygen supply, including the efficiency of the environmental control system and the expected rate of carbon dioxide accumulation. Thermal calculations determine whether temperatures within the spacecraft will remain within tolerable limits. You follow how precise knowledge of chemical reactions, electrical load, and human metabolic requirements informs operational decisions. Each calculation relies on verified physical laws and carefully measured parameters. You follow the crew as they implement improvised solutions. Using available materials and following scientific reasoning, they modify carbon dioxide scrubbers to accommodate different canister shapes. You notice how material compatibility, chemical reactivity, and airflow dynamics are all considered to maintain safe air quality. Even simple mechanical adjustments are guided by an understanding of physics and chemistry, highlighting how foundational scientific principles allow adaptability in critical situations. You track the constant monitoring of electrical systems. Remaining fuel cells continue to operate at partial capacity, and batteries are managed to optimize life support duration. You notice how calculations account for current draw, charge capacity, and efficiency losses. The crew and mission control coordinate carefully, ensuring that energy conservation strategies are both safe and mathematically sound. You sense the quiet discipline required to manage interconnected systems under stress, relying solely on measurable, predictable processes. You observe how the spacecraft's trajectory remains on course despite reduced power. Reaction control systems are used sparingly, with calculations ensuring that small thrusts produce predictable orientation adjustments. Newton's laws continue to govern every motion, and you note the precision required to maintain alignment with the planned translunar path. Even in crisis, the principles of momentum, force, and acceleration provide reliable guidance, allowing human intervention to work in harmony with physical laws. The incident provides a clear lesson in material science, thermodynamics, and systems engineering. You follow how engineers analyze the event to understand failure mechanisms, including thermal expansion, electrical arcing, and structural limits. Calculations determine why the rupture occurred and how similar events can be prevented in future missions. You notice the emphasis on empirical evidence, laboratory testing, and careful observation, illustrating the iterative nature of engineering in the context of space exploration. You watch the crew settle into a steady rhythm of monitoring, adjustment, and observation. Oxygen, power, and thermal conditions are continually tracked. You notice the integration of human judgment with automated measurement systems, each reinforcing the other. Data feeds from sensors are interpreted in real time, allowing controlled responses to dynamic conditions. Even in an environment of extreme risk, the predictable application of science maintains order and safety. You consider the broader implications of the tank failure. Lessons learned in material selection, wiring insulation, and fuel cell integration influence future spacecraft design. Engineering decisions are informed by observed behavior under stress, with attention to tolerances, redundancy, and fail-safe systems. You sense the connection between observation, measurement, and practical application, understanding that knowledge from one event extends to broader principles of spaceflight safety. You feel the calm that comes from understanding how science explains the sequence of events. Pressurized gas behavior, electrical system interactions, and chemical reactions all operate within predictable laws. Even a catastrophic failure is rendered comprehensible through physics, chemistry, and engineering analysis. The spacecraft remains navigable, life support continues, and every action is guided by known scientific principles. The spacecraft continues its journey with measured adjustments, its course toward the moon maintained despite the reduced resources. You notice how gravity, inertia, and momentum continue to guide motion, and how the crew's careful management of oxygen and power allows survival. Each system operates within predictable limits, and the principles of physics provide both guidance and reassurance. The reliability of known laws sustains the crew, demonstrating the practical application of scientific reasoning in the most extreme conditions. You feel the quiet tension inside the spacecraft as oxygen levels remain lower than planned. The crew monitors atmospheric pressure, ensuring that the command module maintains a breathable environment. Carbon dioxide concentration rises steadily, tracked by sensors that measure partial pressure within the cabin. You notice how human respiration and limited air volume interact predictably, allowing precise calculations of how long current oxygen supplies can sustain life. Every measurement provides critical information for planning the next actions. The lithium hydroxide canisters that scrub carbon dioxide become the focus of careful attention. These canisters chemically absorb CO2, using a reaction between lithium hydroxide and carbon dioxide to produce lithium carbonate and water. You follow the reaction closely, observing that the efficiency of removal depends on surface area and airflow through the canister. Engineers calculate how long each canister will function and how multiple units can be combined to manage rising CO2 levels. You see the direct application of chemistry in sustaining life, where predictable reactions allow controlled management of a vital resource. Water and power reserves are continuously monitored. You track the measurements of remaining water, both for consumption and for cooling systems. Every drop is accounted for, as water serves dual purposes for the crew's physiological needs and the spacecraft's thermal management. Electrical systems are carefully regulated, with current draw from batteries calculated against expected discharge rates. You notice how energy conservation strategies become critical, relying on known principles of electricity, thermodynamics, and material efficiency to prolong survival. You observe the crew improvising modifications to the carbon dioxide scrubbers. Using available materials, they adapt canisters from the lunar module to fit the command module, maintaining airflow and reaction efficiency. You notice the careful attention to chemical compatibility, material integrity, and gas flow dynamics. Even small errors could reduce the effectiveness of CO2 removal, yet the modifications follow predictable engineering principles. The process demonstrates the application of physics and chemistry in a practical, life-sustaining context. You track the environmental control system as it circulates air, removes excess heat, and distributes oxygen. Fans move air past sensors and scrubbers, while heaters and radiators maintain a stable temperature. You observe the integration of thermodynamics with fluid dynamics, ensuring that airflow is sufficient to prevent localized oxygen depletion. The crew monitors these systems continuously, making small adjustments based on sensor feedback, demonstrating the predictable relationship between force, flow, and energy transfer in maintaining habitability. The crew organizes power usage carefully. You notice how battery levels are checked and distributed according to priority systems, with critical life support and communication circuits receiving precedence. Calculations ensure that thruster activity and lighting do not exceed available energy. You follow how electrical engineering principles, including current, voltage, and resistance, are applied in real time to maintain balance. The spacecraft functions as a precisely managed network, with energy and resources allocated based on calculated needs. You feel the interplay between human metabolism and environmental conditions. Each astronaut's oxygen consumption, carbon dioxide output, and water usage is tracked with predictable accuracy. You notice how body mass, activity level, and respiration rates are used to calculate remaining resources. Even routine movements are managed to conserve energy and minimize CO2 production. The integration of physiology, chemistry, and physics ensures that survival remains feasible despite reduced resources. You observe the spacecraft's temperature control as it responds to changing heat loads. Thermal energy from electrical systems, solar radiation, and the crew's own body heat is redistributed through conduction, convection via circulating air, and radiation through external panels. Engineers have calculated thermal equilibrium, ensuring that cabin temperature remains within tolerable limits. You follow the precise energy balance, noting how power usage, heat generation, and cooling converge to maintain stability. Every calculation is grounded in well-understood thermodynamic principles. The crew measures oxygen levels continuously. You notice how sensors detect partial pressure and flow rates, ensuring that readings match expected values for breathable air. Adjustments are made using valves and pumps to redistribute oxygen between modules. The mathematics of gas laws, including pressure, volume, and temperature, guide these decisions. You see how the predictable behavior of gases allows engineers to maintain a safe environment, even with limited reserves and partial system failures. Water purification systems are monitored with equal care. You observe how condensed moisture is collected and filtered for reuse. Calculations account for humidity, consumption, and heat removal, maintaining both water quality and thermal stability. You notice how chemical and mechanical systems interact, with predictable efficiencies guiding resource management. The crew relies on exact measurements, demonstrating how applied chemistry and engineering principles sustain life over extended periods in space. You track the ongoing monitoring of carbon dioxide scrubbers. Engineers calculate the cumulative exposure of each canister, estimating remaining capacity. You notice the methodical approach to scheduling swaps and airflow adjustments, ensuring that CO2 concentration remains within safe limits. Chemical kinetics and fluid dynamics provide predictable outcomes, allowing controlled maintenance of the cabin atmosphere. The crew operates within these calculated margins, using reliable science to guide every action. The spacecraft moves along its translunar trajectory with minor adjustments. You notice that the life support systems continue to function predictably despite reduced power and oxygen. Thruster firings are minimized to conserve resources, guided by Newtonian principles of motion. You see how momentum, mass, and applied force interact to allow controlled course corrections without unnecessary energy expenditure. Even routine orientation adjustments are calculated carefully, integrating physics, engineering, and human planning. You observe the crew performing basic scientific observations. Instruments measure cosmic rays, solar radiation, and temperature changes within the cabin. Data are logged and transmitted to Earth, integrating with mission controls calculations. You notice how predictable physical laws allow both measurement and correction, ensuring safety and continuity. The interplay of observation, calculation, and intervention highlights the methodical application of science to maintain stability in an environment where resources are constrained and consequences are immediate. You feel the calm order of ongoing monitoring. Oxygen, water, and energy remain limited but managed precisely. Every adjustment follows predictable principles, whether chemical, mechanical, or electrical. The crew's activity is measured, deliberate, and guided by well-understood laws. You sense the quiet confidence that comes from knowing that science, applied consistently, provides reliable support even in extreme circumstances. As the spacecraft continues its flight, you note how life support calculations intersect with motion through space. Newton's laws, thermodynamics, chemical reactions, and electrical engineering converge to maintain equilibrium. The crew, instruments, and systems operate as a coordinated unit, relying on the predictable behavior of matter and energy. Each decision reinforces the practical power of science to sustain life, allowing humans to survive in an environment far removed from Earth. You feel the spacecraft glide smoothly through space, coasting along the translunar path. Instruments display velocity, position, and orientation with constant updates. You notice how small adjustments can produce large effects over distance and time. Each thruster firing is carefully calculated to modify the spacecraft's trajectory by fractions of a degree. You observe the precise relationship between applied force, spacecraft mass, and resulting acceleration, demonstrating Newton's second law in practice. Even minor errors in timing or magnitude are avoided through meticulous calculation and verification. The crew coordinates with mission control to review the free return trajectory. This trajectory is designed so that if no further maneuvers are made, the spacecraft's path will naturally loop around the Moon and return to Earth. You track how orbital mechanics are applied, considering the relative positions of Earth and Moon, gravitational influences, and the spacecraft's momentum. Calculations incorporate mass, speed, and distance to predict position at future points. You see how the principles of motion, combined with careful measurement, provide a predictable, fail-safe path that increases the crew's safety. You observe the first course correction. Small thrusters are fired in short bursts, precisely timed to adjust the spacecraft's velocity. You notice how acceleration is measured in millimeters per second, yet over thousands of kilometers, these adjustments alter the path significantly. Engineers and astronauts calculate the duration, magnitude, and direction of each burn, relying on known laws of motion. You follow how the combined effects of gravity, inertia, and thrust interact, producing a controlled change in trajectory that maintains the intended free return path. The crew continuously monitors fuel levels. You notice how propellant is divided between the main engine and reaction control systems. Each maneuver considers not only trajectory but also conservation of fuel, balancing immediate adjustments with long-term requirements. Calculations account for efficiency, gravitational influence, and the spacecraft's remaining mass. You sense the precision of planning, where careful application of energy and momentum allows the spacecraft to follow its intended path while preserving resources for later maneuvers. You track how gravitational interactions influence the trajectory. The Earth's pull gradually diminishes, while the Moon's gravity begins to curve the spacecraft's path. You observe how mission planners calculate the timing and magnitude of thruster burns to take advantage of gravitational assists. Even without continuous propulsion, predictable forces guide motion, allowing the spacecraft to coast along a safe path. You follow how calculations of acceleration, velocity, and distance are integrated to maintain an efficient, controlled trajectory. The crew monitors velocity relative to both Earth and Moon. Instruments report both linear speed and angular orientation. You notice how the spacecraft's velocity vector is adjusted by carefully applied thrusts. The result is a precise path that maintains the free return loop while positioning the spacecraft for potential lunar orbit or observations. You track how small adjustments are multiplied over the distance traveled, demonstrating the cumulative effect of controlled acceleration in space. You observe the spacecraft's orientation adjustments. Using reaction control thrusters, the crew rotates the vehicle to align engines with the intended vector. You notice how torque, angular momentum, and center of mass calculations determine the correct firing sequence. Even a slight misalignment could reduce the efficiency of a burn, requiring additional fuel consumption. You see the combination of mechanical principles and careful monitoring ensuring that orientation and trajectory remain consistent with predictive calculations. The crew performs calculations to verify predicted position. Instruments measure distance to the Moon, relative velocity, and trajectory angle. You follow the integration of these measurements with orbital mechanics equations, determining when and how to execute minor burns. You notice how mass, acceleration, and gravitational pull combine predictably to maintain the free return path. The spacecraft's position is continuously verified, with every adjustment informed by established physical laws rather than guesswork. You notice the crew working with mission control to confirm tolerances. Calculations include safety margins for timing errors, variations in mass, and small discrepancies in gravitational influence. Even when uncertainties exist, the spacecraft's trajectory is robust, thanks to predictable orbital dynamics. You track how engineers and astronauts cross-check multiple data sources, ensuring that each adjustment maintains the integrity of the mission's path. Every decision is grounded in well-understood physics, reducing risk through calculation rather than assumption. You observe the second course correction, executed to refine the path as the spacecraft approaches lunar influence. Thrusters fire for measured intervals, producing precise changes in velocity and direction. You notice the coordination required between onboard measurements and calculations performed on Earth. Each thruster pulse is informed by the spacecraft's mass, expected gravitational influence, and current trajectory. You see the predictability of motion when force, mass, and time are applied correctly, demonstrating the reliability of Newtonian mechanics in interplanetary navigation. You track the spacecraft as it continues to coast along the adjusted trajectory. Microgravity affects the crew, yet daily routines continue. Instruments monitor oxygen levels, carbon dioxide, power consumption, and thermal conditions. You notice how life support systems operate predictably, and minor trajectory adjustments do not disrupt environmental stability. Calculations of resource use integrate with navigational plans, showing how the principles of physics, chemistry, and engineering converge to maintain both motion and habitability. The spacecraft passes the halfway point toward the Moon. You observe how gravity from both Earth and Moon affects velocity, with momentum carrying the spacecraft along a natural arc. You notice how precise calculations allow prediction of arrival time and location, minimizing the need for additional adjustments. Each small thruster burn is carefully timed to maintain trajectory while conserving fuel, demonstrating the interplay between applied mechanics and resource management. You follow the crew as they check the alignment of communication antennas. Data transmitted to Earth provides feedback on trajectory accuracy. You notice how signal travel time is calculated, as radio waves move at the speed of light, creating a slight delay that must be accounted for in instructions and telemetry interpretation. The crew applies predictable, measured corrections, confirming that both physical and temporal principles govern interactions between spacecraft and mission control. You notice the spacecraft gently curving toward lunar influence, maintaining the free return corridor. You follow the calculations that ensure the moon's gravity will assist rather than destabilize the path. You sense the predictable precision of interplanetary motion, where mass, velocity, and gravitational fields interact according to established laws. The crew's careful monitoring and adjustments ensure that these predictable forces guide the spacecraft safely, highlighting the consistent reliability of physics across vast distances. You feel the quiet rhythm of coasting, monitoring, and minor adjustments. Instruments, thrusters, and life support systems work together in harmony, grounded in predictable principles. You notice how mass, energy, and force interact to maintain trajectory, and how the crew's careful calculations ensure safety. Even in the vacuum of space, the laws of motion govern the journey, allowing the spacecraft to glide steadily along its path toward the moon. You feel the quiet intensity of the control room, filled with consoles, screens, and the soft hum of data flowing from space. Telemetry streams arrive continuously, displaying oxygen pressures, fuel cell outputs, temperatures, and spacecraft orientation. Each value represents a precise physical measurement transmitted across hundreds of thousands of kilometers. You notice how controllers cross-check readings from multiple sources, ensuring that any anomaly is verified before decisions are made. This constant monitoring transforms raw numbers into actionable understanding, allowing human judgment to interact seamlessly with technology. You observe the arrangement of mission control as teams specialize in different systems. Electrical engineers track power flow through the spacecraft's batteries and fuel cells, noting fluctuations caused by environmental changes or system adjustments. Environmental specialists watch oxygen and carbon dioxide levels, temperature, and humidity, calculating how the crew's metabolic needs interact with limited supplies. Navigation officers monitor the trajectory, predicting the spacecraft's position based on precise calculations of velocity, gravity, and accumulated course corrections. You notice the methodical division of expertise, each team providing critical insight into a complex system of interdependent variables. Simulations run continuously in the background. You follow how controllers practice potential contingencies, ranging from minor sensor errors to major system failures. Every scenario is calculated in advance, using precise physics and engineering principles to predict outcomes. When the oxygen tank ruptured, these simulations allowed rapid assessment of resource depletion, power reduction, and environmental risk. You notice how prior preparation and repetitive rehearsal transform uncertainty into predictable action. The interplay between observed data and prior simulations provides a calm, systematic approach to managing real-time emergencies. You watch the communication loops connecting the spacecraft and mission control. Radio signals transmit voice, telemetry, and instructions with slight but predictable delays caused by the finite speed of electromagnetic waves. Controllers calculate timing adjustments to account for these delays, ensuring that instructions are received and understood accurately. You observe the precision required for this coordination. A delay of a few seconds might not matter for conversation, but for trajectory adjustments, every fraction of a second counts. You sense the reliability of physics in guiding communication across space. Data analysis occurs continuously, with engineers processing telemetry to detect deviations from expected norms. You notice algorithms flagging minor discrepancies, which humans then evaluate in the context of mission parameters. Each data point represents physical phenomena, pressure, temperature, electrical current, or velocity, allowing precise interpretation using established laws of physics and chemistry. You follow how subtle changes in readings prompt adjustments, with every action grounded in empirical evidence rather than conjecture. Teamwork is central to the room's operations. You observe how specialists exchange information, confirm observations, and propose solutions collaboratively. Calculations are shared, verified, and applied systematically. You notice the calm efficiency, where urgency is balanced with methodical verification. Human cognition is supported by computational tools, yet every intervention is filtered through experience and rigorous scientific reasoning. The integration of human skill with precise measurement demonstrates how engineering, physics, and applied mathematics converge in real-time problem-solving. You see the flow of decision-making during the oxygen crisis. Controllers evaluate remaining supplies of oxygen, power, and water, applying principles of thermodynamics, fluid dynamics, and chemical kinetics to predict how long the crew can remain safe. You follow how calculations consider metabolic consumption, scrubber efficiency, and energy reserves. The process is iterative. Prediction, verification, adjustment, and communication occur in a continuous cycle. You notice how the predictability of physical laws allows decisions to be made calmly, even under potentially life-threatening conditions. Redundant systems provide an additional layer of security. You track how backup power, alternative oxygen supplies, and secondary communication channels are monitored and activated when needed. You observe the engineering principles underlying redundancy. Multiple independent systems reduce the risk of simultaneous failure. Each system operates according to the same predictable laws of physics and chemistry as the primary systems, allowing mission control to rely on backups without uncertainty. You sense the reliability this design brings, even as data from a compromised system continues to flow. You notice how training prepares controllers for these high-stakes moments. Years of simulation and experience allow rapid interpretation of complex data. You follow how repeated exposure to scenarios builds mental models of cause and effect, enabling immediate recognition of patterns. Even when real conditions differ slightly, the underlying physics remains constant, and these models guide decision-making. You see the interplay of human learning, system understanding, and scientific principle forming a foundation for effective management of extreme situations. Problem-solving is both systematic and flexible. You observe controllers considering multiple potential interventions, evaluating predicted outcomes using calculations and empirical knowledge. Each decision is weighed for its effect on oxygen, power, trajectory, and thermal stability. You notice how this process blends computational modeling with real-time observation, allowing adaptation to the spacecraft's evolving state. Physics and engineering guide each option, ensuring that interventions are safe, effective, and grounded in verifiable principles. You watch the crew following instructions with precision. Each procedure is communicated clearly, with timing, sequence, and method calculated to minimize risk. You observe how mission control and the spacecraft operate as an integrated system, with data flowing in both directions. The combination of human expertise, technological monitoring, and physics-based reasoning allows rapid yet accurate responses, preventing escalation of emergencies. Every adjustment follows a chain of predictable cause and effect, demonstrating the practical application of scientific knowledge. The atmosphere in the control room is calm but focused. You notice the interplay of attention, experience, and scientific understanding, creating a structure capable of responding to high-pressure situations. Telemetry continues to flow, each number representing a physical measurement, each calculation grounded in predictable laws. You follow the way information is interpreted, cross-checked, and applied, providing a model of organized human response supported entirely by science. You observe how mission control continuously plans for contingencies. You notice the calculations involved in predicting oxygen depletion, electrical load, thermal shifts, and trajectory adjustments. Each factor is modeled using physics, chemistry, and engineering principles. You see how the integration of measurement, calculation, and communication creates a system in which risk is managed, even in situations where immediate danger exists. The combination of preparation, observation, and applied science allows the crew to remain safe despite equipment failures. You feel the calm efficiency of the room as data continues to flow and decisions are made. Telemetry, calculations, and experience combine to maintain spacecraft integrity and crew safety. You notice how scientific principles underpin every action, ensuring that human judgment complements predictable physical laws. The precise coordination of observation, analysis, and intervention demonstrates the power of organized knowledge applied under pressure. You feel the spacecraft shift as the crew prepares to power down the command module and transfer essential systems to the lunar module. The LM was designed for short stays on the moon's surface, yet it now must sustain 3 astronauts for several days in space. You notice how engineers quickly calculate oxygen usage, water availability, and battery capacity to ensure survival. The limited volume and resources require precise allocation, where every calculation is informed by principles of chemistry, physics, and human physiology. The oxygen supply is the first critical consideration. You observe how the LM's tanks, originally intended for 2 astronauts during lunar operations, are recalculated to support 3 for an extended period. Engineers and astronauts assess the capacity using flow rates, cabin volume, and consumption rates based on metabolic needs. You notice the predictable relationship between pressure, volume, and gas consumption governed by the ideal gas law. Each adjustment is precise, ensuring that oxygen levels remain sufficient until the spacecraft can return to Earth. Carbon dioxide removal becomes a critical focus. The LM's environmental system contains scrubbers designed for lunar excursions, but the increased crew load and extended duration require modification. You follow how lithium hydroxide canisters are repurposed from both the LM and the command module to maintain safe CO2 levels. Airflow through these canisters is optimized using measured ducting and timing. You notice the chemical reaction between lithium hydroxide and carbon dioxide, which produces lithium carbonate and water, and how surface area and airflow are carefully controlled to maximize efficiency. Power management is another major concern. You track the energy available in the LM's batteries, which were designed for shorter missions and limited maneuvering. Every thruster pulse, environmental system operation, and electrical instrument draw is accounted for. You observe how engineers calculate total load, factoring in power consumption per hour, battery discharge curves, and conversion efficiency. The crew adjusts routines to conserve energy, turning off non-essential systems and scheduling high-power operations to align with available reserves. Thermal control is carefully monitored. You notice how the LM's insulation, radiators, and heaters are repurposed to maintain a livable temperature. Calculations consider heat generated by the crew and electrical systems versus heat lost to the surrounding space. The predictable transfer of thermal energy allows engineers to anticipate temperature fluctuations and adjust heater output or circulation fans accordingly. You follow the interplay of conduction, convection within the cabin, and radiation through the module walls, appreciating how thermodynamics guides survival strategies. The crew reorganizes the interior to optimize space and movement. You notice how life support systems are positioned to allow efficient airflow through scrubbers and maintain even temperature distribution. Instruments are relocated to conserve power and reduce interference. Every adjustment is informed by physics, including airflow dynamics and weight distribution, ensuring the LM remains stable under acceleration or minor orientation changes. You sense the deliberate precision of each action, guided entirely by engineering reasoning. Water usage is monitored closely. You track how existing water supplies are rationed, with consumption calculated based on crew metabolism, temperature regulation, and humidity control. Condensed moisture from air circulation is reclaimed when possible. You notice how the physical properties of water, its heat capacity, phase changes, and density, are applied to manage both hydration and cabin temperature. The crew's careful attention ensures that resources are neither wasted nor exceeded, relying entirely on predictable physical principles. You observe the use of the LM's propulsion system. Reaction control thrusters are operated sparingly to adjust orientation and maintain stability. Each maneuver is calculated based on mass, thrust, and required delta V, applying Newton's laws with precision. You notice that even small bursts affect orientation significantly in microgravity, requiring careful planning to avoid unnecessary energy expenditure. Thruster operations are integrated with life support needs, ensuring that propulsion does not compromise oxygen, power, or temperature. The crew monitors CO2 levels continuously. You follow how measurements inform airflow adjustments and scrubber placement. Each observation allows for incremental modifications to maintain a breathable environment. You notice the cumulative effect of chemical reactions and airflow, which can be modeled predictably using known principles of chemistry and fluid dynamics. The system operates within predictable parameters, and each adjustment ensures stability, highlighting the reliability of applied science in life-critical situations. You watch the coordination between the LM and mission control. Engineers on Earth calculate oxygen depletion, energy use, and thermal balance, communicating corrections to the crew. You notice how telemetry provides continuous verification, allowing adjustments to align with real-time conditions. Calculations of resource consumption, energy expenditure, and chemical reaction efficiency are continually cross-checked. You observe the integration of human expertise, automated monitoring, and scientific principles to maintain equilibrium, demonstrating the predictive power of physics and chemistry in a constrained environment. The crew implements strict rationing of food and water. You notice how caloric intake is calculated to match metabolic needs while minimizing waste. The physical principles of energy transfer within the body, combined with predictable chemical reactions in metabolism, inform consumption planning. You follow how even simple acts, such as heating food or using water for rehydration, are managed to conserve energy and maintain life support integrity. Every decision reflects a deep reliance on established scientific knowledge. Orientation adjustments are performed to optimize solar exposure for electrical generation and thermal control. You track calculations of angular momentum, torque, and gravitational influence from both Earth and Moon. Even minor rotations are guided by physics, ensuring that energy generation and thermal stability are not compromised. You notice the precision required for these maneuvers, where predictable outcomes are achieved by strictly adhering to Newtonian mechanics. The crew maintains psychological and physical well-being within the LM's confined environment. You observe the importance of routine, minimal exertion, and careful planning. Even movement is calculated to conserve oxygen and energy. You notice how predictable physiological needs intersect with the LM's life support systems, requiring continuous adjustment of oxygen, temperature, and carbon dioxide scrubbing. Scientific understanding of metabolism, respiration, and material limits guides all activity, ensuring survival under extreme conditions. You feel the quiet rhythm of life inside the LM. Systems hum steadily, readings remain within calculated margins, and the crew's movements are deliberate. You notice how the predictable operation of mechanical, chemical, and electrical systems allows for a controlled environment despite limited resources. Each adjustment, calculation, and observation reinforces the application of science to maintain life, demonstrating the critical role of engineering flexibility in survival situations. You reflect on how the LM, though originally intended for lunar excursions, provides a safety net through careful scientific management. Its systems, when repurposed with precise calculations and methodical observation, create a livable environment despite constraints. You notice how physics, chemistry, and engineering principles are integrated in real time, forming a reliable support network. The LM's adaptation demonstrates the power of applied science to overcome unexpected challenges. You notice how life aboard the spacecraft is governed by careful planning. Every resource, water, food, oxygen, and electrical power, is monitored in real time. You see how measurements are taken continuously, using sensors and manual logs to verify consumption and remaining reserves. Each resource has a predictable rate of usage based on physical laws, human metabolism, and system efficiency. You follow calculations of energy flow, mass distribution, and thermal load to ensure that every system continues to function effectively. Water is the first resource you observe in detail. You notice how the crew tracks daily intake, using precise measurements for drinking, cooking, and minimal hygiene needs. Condensation from air circulation and the spacecraft's environmental systems is reclaimed, filtered, and reused. You see how phase changes, density, and heat capacity are applied to manage water safely and efficiently. Each liter is accounted for, demonstrating the predictable principles of thermodynamics and fluid dynamics applied to maintain life in a closed system. Food is rationed with careful attention to caloric needs. You follow calculations of energy expenditure based on activity level, body mass, and environmental conditions. Each portion is measured to provide sufficient energy while minimizing waste. You notice how the chemical composition of food, carbohydrates, proteins, and fats is considered to maintain metabolism and prevent nutrient imbalance. The process demonstrates the application of biochemistry and physics, linking energy transfer in the body with the resources available on board. Electricity is managed with equal precision. You track the flow of power from batteries and solar panels, observing how voltage, current, and resistance are monitored for every system. Each electrical draw, from lighting to life support, is calculated to ensure that energy is available when needed most. You notice how conservation strategies like powering down non-essential instruments extend operational time. The predictable behavior of electrical circuits allows engineers to plan consumption accurately, ensuring that the spacecraft remains functional despite limited supply. You observe oxygen management as an ongoing calculation. Partial pressure sensors measure the concentration in the cabin, while scrubbers remove carbon dioxide to maintain a breathable environment. You follow how crew activity is adjusted to minimize oxygen use and CO2 production. Even minor movements are considered in planning, demonstrating the predictable relationship between metabolism, respiration, and air quality. Each adjustment reinforces the way chemical and physical principles sustain life in a confined environment. Thermal control is interwoven with resource management. You notice how electrical energy contributes to heating, while environmental systems circulate air to distribute temperature evenly. You follow how the spacecraft's insulation, heat sinks, and radiators maintain stable conditions. Calculations of thermal energy transfer, using conduction, convection, and radiation principles, ensure that resources are used efficiently while maintaining crew comfort. The integration of these calculations with life support management demonstrates a layered application of physics. You track waste management and recycling. Urine is collected and processed, while condensation and humidity are reclaimed. You notice how chemical and physical processes, filtration, absorption, and phase change, allow resources to be recovered for use in water systems. Each step follows predictable principles with measurable efficiency and clear limits. You follow how engineering design allows closed-loop systems to maintain sustainability, even with extremely limited mass and volume available. Inventory control is continuous. You notice how the crew maintains strict logs, noting every item's location, mass, and intended use. Each object is positioned to prevent imbalance and minimize movement during maneuvers. You observe how distribution of mass affects spacecraft orientation and stability, demonstrating the application of mechanics in a practical setting. Calculations of center of mass and moments of inertia guide placement and movement, ensuring that small adjustments do not require unnecessary thruster use or energy consumption. You observe energy management during daily activities. Heating water, operating computers, or conducting experiments requires careful timing. You notice how schedules are optimized to align high-energy tasks with periods of maximum battery capacity. You follow calculations of load, expected voltage drop, and system efficiency, showing how physical laws of electricity and energy conservation inform practical decision-making. Even routine activity becomes an applied exercise in physics. You notice the interaction between human physiology and resource planning. Oxygen consumption, hydration needs, and caloric intake are all predictable, based on known metabolic rates. You follow how engineers calculate safe limits for each system, allowing for both expected activity and minor emergencies. This integration of biology with engineering ensures that the crew can maintain health while conserving critical supplies. Measurements and predictions form a feedback loop, ensuring that systems and human needs remain balanced. You observe the crew adjusting routines to optimize efficiency. Exercise, work, and rest periods are scheduled to minimize energy consumption and oxygen use. You notice how each choice, when to use lighting, when to operate instruments, affects overall resource management. Calculations of thermal output, electrical load, and air quality ensure that every action is consistent with maintaining stability. Predictable patterns of behavior reduce strain on systems, showing how applied science shapes daily life in space. Communication with mission control integrates resource monitoring with trajectory and life support management. You follow how telemetry provides data on battery levels, oxygen pressure, and thermal conditions. Engineers cross-check sensor readings with expected values, ensuring that calculations of consumption remain accurate. You notice how the predictability of physical laws allows both crew and control teams to anticipate needs, adjust operations, and prevent emergencies before they arise. You track how resource allocation adapts to changing conditions. Unexpected increases in CO2 levels or temperature require recalculation of oxygen flow, battery use, or water consumption. You observe how physics, chemistry, and engineering principles guide responses, with predictable results based on accurate measurement and modeling. Each decision relies on established knowledge of material properties, energy transfer, and metabolic processes. You notice the quiet precision with which the crew follows procedures. Every adjustment, every calculation, and every conservation effort demonstrates the application of scientific understanding. You follow how engineering principles, physics laws, and biological data converge, maintaining equilibrium in a resource-limited environment. Predictable outcomes arise from careful planning, methodical observation, and the disciplined application of science. You feel the spacecraft's controlled rhythm, with life support systems, electrical systems, and human activity coordinated to maximize efficiency. You notice how interconnected calculations guide daily routines, ensuring that oxygen, water, power, and food remain sufficient. The crew's actions are deliberate, each movement and measurement reinforcing the role of science in maintaining life. You feel the spacecraft orient itself for re-entry, carefully aligning along a pre-calculated trajectory. Instruments display velocity, angle of descent, and atmospheric density, continuously updated from sensors and predictive models. You notice how a shallow angle prevents skipping off the atmosphere, while a steep angle would increase heating and stress. Every calculation is informed by Newton's laws of motion and principles of orbital mechanics. You follow the precise adjustments the crew makes, ensuring that the spacecraft will enter Earth's atmosphere safely. As the spacecraft approaches the upper layers of the atmosphere, you observe the first interactions with air molecules. The velocity of the capsule converts kinetic energy into thermal energy through friction and compression of the air. You notice the predictable relationship between speed, atmospheric density, and heat generation. The heat shield, composed of ablative material, begins to absorb and redirect this energy. The surface gradually erodes in a controlled way, carrying away heat while preventing excessive temperatures from reaching the interior. This process follows thermodynamic principles that convert mechanical energy into heat while maintaining material integrity. You observe the forces acting on the spacecraft. Deceleration occurs as drag increases with denser atmospheric layers. You notice how the crew experiences g-forces, the result of rapid changes in velocity. These forces are calculated in advance, based on mass, velocity, and atmospheric resistance. You follow how the predictable relationship between force, mass, and acceleration, described by Newton's second law, governs both the spacecraft and the human bodies inside. Straps, seat orientation, and cushioning are designed to distribute these forces safely. Temperature gradients along the heat shield are monitored in real time. You notice how thermal sensors detect heating rates, allowing engineers to verify that the material performs as expected. Heat transfer occurs primarily through conduction within the shield and radiation to the surrounding atmosphere. You follow calculations of thermal conductivity, specific heat, and heat flux, which determine material choice, thickness, and shape. These physical principles ensure that internal temperature remains within survivable limits while dissipating the intense energy of re-entry. The spacecraft's angle of attack is maintained with small adjustments using reaction control thrusters. You observe how torque, angular momentum, and orientation interact to keep the capsule aligned properly. Even minor misalignments could increase stress on the heat shield or create off-axis forces, demonstrating the predictable importance of rotational dynamics. You notice how the crew applies calculated control inputs to maintain stability, guided entirely by physics and precise instrumentation. You follow the transition from the near vacuum of space into increasingly dense atmospheric layers. Air density rises predictably, affecting deceleration and thermal loads. You notice the relationship between atmospheric pressure, drag force, and velocity, which can be described mathematically and predicted accurately. The spacecraft slows gradually, but kinetic energy remains substantial, requiring careful consideration of all physical forces involved. You track how mass, speed, and resistance are combined to determine stress on both structure and occupants. You observe the shockwave forming in front of the capsule. High-velocity air compresses and heats rapidly, creating a layer of plasma surrounding the heat shield. You follow calculations of ionization, temperature, and pressure in this layer, understanding how it reduces energy transfer to the spacecraft's surface. Even the glowing plasma adheres to predictable physical laws, where molecular collisions and energy dissipation follow thermodynamic principles. This controlled interaction protects the spacecraft and crew while demonstrating real physics at work. Parachute deployment occurs at a calculated altitude, slowing descent further. You notice how drag from the parachutes reduces velocity according to the area of the canopy, air density, and descent speed. Forces are distributed across attachment points, with predictable tension calculated to avoid structural failure. You follow the progression from main chute deployment to stabilization, observing how fluid dynamics and materials engineering work together to manage energy safely. Each stage of deceleration is carefully timed, using physics to predict exactly when the spacecraft will reach a safe splashdown speed. You track the capsule's rotation during descent. You notice small oscillations which are damped by drogue chutes and aerodynamic design. Calculations of angular velocity, torque, and damping coefficient predict the behavior of the system. Even minor variations can be anticipated and corrected with pre-calculated control measures. You see how predictable physical laws allow the spacecraft to remain stable despite forces from wind, air currents, and drag. The integration of mechanics and material science ensures that the capsule remains properly oriented for final descent. You observe temperature measurements inside the cabin as deceleration increases. Heat is managed by insulation and by energy absorption in the heat shield, preventing dangerous increases. You follow the predictable conversion of kinetic energy into thermal energy, which is carefully managed by engineering systems. The interplay of mass, velocity, and atmospheric density governs how much energy is transferred, illustrating practical applications of mechanics and thermodynamics in protecting both structure and crew. Telemetry confirms expected performance. You notice how engineers compare predicted deceleration, heating, and orientation with real-time data. Calculations of drag, g-forces, and thermal flux match closely with observations, reinforcing the reliability of Newtonian physics and thermodynamics. Even in the dynamic, high-energy environment of re-entry, predictable principles allow the spacecraft to maintain its intended course safely. Deviations are minor and within calculated tolerances, showing the precision of design and execution. You observe how the crew maintains position and posture to manage forces. Body orientation, seat restraints, and harness tension distribute g-forces predictably. You notice the correlation between predicted acceleration, measured velocity reduction, and internal forces. Human physiology interacts with physics in a controlled environment, demonstrating how knowledge of mechanics and biological limits informs spacecraft design and crew procedures. The final stages of descent are guided by precise timing and measurement. Drag continues to slow the capsule until velocity is compatible with safe water impact. You track the predictable effect of atmospheric density, parachute area, and descent speed on final kinetic energy. Calculations ensure that the capsule's motion is gradually brought under control, minimizing risk of structural damage or injury. Physics provides a reliable framework for every decision and adjustment during this intense phase of flight. You feel the gradual transition from high-speed, high-energy descent to calm floating above the ocean. Forces are reduced, temperatures stabilize, and the capsule maintains proper orientation. You notice how predictable interactions of drag, mass, velocity, and materials properties result in a controlled, survivable landing. The crew's understanding and application of physics, combined with engineering precision, govern each step, illustrating the practical reality of spaceflight's final challenge. You see the capsule approaching the ocean surface, slowed by parachutes and oriented precisely for impact. Velocity has been reduced from orbital speed to a controlled descent rate, calculated to minimize structural stress and crew risk. You notice how the water's density and surface tension interact with the capsule's shape, producing predictable deceleration forces on contact. Engineers have calculated the expected impact pressure, ensuring the capsule floats safely while absorbing kinetic energy. Buoyancy becomes immediately apparent. The spacecraft's center of mass and volume are designed to allow it to float upright, even in variable sea conditions. You follow the predictable application of Archimedes' principle. The upward buoyant force equals the weight of the water displaced by the submerged portion of the capsule. This ensures stability and prevents tipping. You notice how flotation devices and air pockets within the structure contribute to maintaining this balance, demonstrating practical use of physics in real-world conditions. Water dynamics play a critical role as the capsule settles. You observe how waves and currents interact with the hull, producing oscillations that are damped by the capsule's mass and shape. Calculations of drag and oscillatory motion ensure that forces remain within tolerable limits. Even small deviations are predictable based on fluid dynamics and the predictable properties of water, allowing recovery teams to anticipate movements and secure the spacecraft efficiently. The recovery team approaches with helicopters and ships. You notice how the physics of motion, buoyancy, and leverage are considered when connecting lines to lift the capsule. Calculations of mass distribution, tension, and torque ensure that the spacecraft can be hoisted without structural compromise. Each step applies principles of mechanics, ensuring that forces acting on both the capsule and personnel remain within safe limits. You follow the precision and predictability of these operations, grounded entirely in established physical laws. Medical evaluations begin immediately. You observe how human physiology is assessed following exposure to G-forces, microgravity, and re-entry stresses. Heart rate, blood pressure, oxygen saturation, and muscle function are measured to ensure that the crew has tolerated deceleration and splashdown. You notice how predictable physiological responses, based on prior research and known human limits, guide the timing and procedures of these evaluations. Calculations of fluid balance, metabolic stress, and vestibular function inform each step, reflecting the intersection of biology and physics. Handling the spacecraft after splashdown involves careful movement and stabilization. You see how engineers consider center of mass, torque, and buoyant forces to prevent capsizing or unnecessary strain on structural components. Lines and harnesses are attached according to calculated angles and tension, distributing forces evenly. You notice that these procedures rely entirely on classical mechanics, where predictable relationships between force, mass, and displacement guide safe operations. You follow the environmental considerations for the spacecraft. Saltwater exposure, temperature gradients, and humidity are monitored to prevent corrosion and degradation. Physical and chemical principles govern the diffusion of water into materials, the rate of oxidation, and thermal expansion. Engineers calculate expected stresses and implement protective measures, demonstrating the integration of materials science, chemistry, and physics in preserving spacecraft integrity. Crew extraction is performed systematically. You observe how harnesses and ladders are deployed, considering forces on the human body and stability of the capsule. Calculations of load distribution and leverage ensure that each astronaut can be moved without injury. Even small angles and positions are predicted using mechanics principles, showing the careful application of physics to human interaction in dynamic environments. You notice how the spacecraft's instrumentation continues to provide readings even after water contact. Telemetry allows engineers to verify system performance and detect any anomalies. Calculations of voltage, pressure, and temperature are compared with expected values, demonstrating the predictable behavior of both mechanical and electrical systems under changing environmental conditions. Data collected during recovery informs engineering improvements for future missions. Environmental monitoring extends to waves, wind, and currents. You observe how the recovery team calculates expected motion of the capsule, using fluid dynamics and statistical models to predict oscillations and drift. Buoyancy combined with wave interaction is considered in the timing and positioning of lifts, allowing controlled movement to the recovery ship. These calculations demonstrate the application of physics to real-world operations, where water, mass, and force interact predictably. You follow the secure transfer of the crew to the ship. Their position and movement are guided by calculations of center of mass and leverage to prevent tipping of the capsule. You notice how restraint systems, seating, and harnesses work together with human motion to minimize forces during lifting and transfer. Predictable outcomes result from careful application of Newtonian mechanics, ensuring both safety and efficiency. Post-recovery checks involve inspection of structural and mechanical systems. You observe how engineers measure hull integrity, parachute lines, flotation devices, and heat shield materials. Calculations of stress, strain, and corrosion potential guide evaluation and maintenance. Each assessment is grounded in material science, mechanics, and chemistry, demonstrating how physics governs both operational performance and long-term durability. Crew well-being continues to be monitored. You notice how predictable aspects of human physiology, such as cardiovascular adaptation, hydration, and muscle tone, inform procedures for reacclimating to gravity. Each intervention is based on prior data, demonstrating the integration of biology with engineering and physics to maintain health. Calculations of expected strain and recovery time allow safe reintroduction to Earth's environment. You observe the systematic documentation of recovery operations. Every procedure, measurement, and observation is recorded, providing a reference for engineering improvements and scientific analysis. Calculations, measurements, and observed outcomes allow engineers to refine predictive models for future missions. You see how iterative observation and empirical validation form the backbone of spacecraft design and operational safety. The spacecraft is finally secured on the recovery ship. You notice how forces are evenly distributed, flotation stability is maintained, and environmental conditions are controlled. Sensors continue to provide feedback, confirming that structural integrity has been preserved. Calculations of torque, tension, and buoyancy guide each final adjustment, showing the application of mechanical and fluid principles in practical recovery operations. You sense the seamless integration of physics, biology, and engineering. From deceleration in the atmosphere to floating in the ocean, every action and adjustment follows predictable laws. Telemetry, force distribution, buoyancy, and physiology combine to maintain safety and operational success. Observing these interactions, you see how decades of research, careful calculation, and practical application converge to conclude the mission with precision. You begin by examining the sequence of events during Apollo 13, following telemetry and recorded communications. Each alert, adjustment, and calculation is logged and time-stamped, providing a precise account of what occurred. You notice how engineers on Earth and the crew in space responded systematically to each situation, guided entirely by known physical principles and technical procedures. The timeline is predictable and verifiable, and every action corresponds to real-world data. You compare this with the cinematic depiction, noting where dramatization emphasizes suspense. You observe how filmmakers compress hours of deliberation into minutes, heighten reactions, or simplify technical dialogue. While the dramatization enhances storytelling, it often omits the methodical calculations that ensured survival. You notice that in reality, each decision was grounded in physics, chemistry, and engineering principles rather than improvisational heroics. Telemetry data reveals the precise behavior of spacecraft systems. You follow oxygen tank pressure readings, battery voltage levels, and the functioning of life support systems. Each change occurs according to predictable physical laws. In the movie, these data are often represented visually or through dialogue for narrative effect, sometimes exaggerating urgency. You see that real events unfolded according to measured variables, confirming that survival depended on predictable, verifiable science rather than suspenseful improvisation. Communication sequences illustrate the methodical nature of problem-solving. You track voice recordings between mission control and the crew, noting clear instructions, responses, and confirmations. You see how information is cross-checked, calculations are verified, and procedures are repeated to reduce error. In cinematic portrayals, these exchanges are condensed or dramatized for pacing. The underlying reality is far more deliberate and measured, demonstrating the consistent application of engineering principles in real time. You study the behavior of the spacecraft under stress. Oxygen depletion, carbon dioxide accumulation, and power limitations occur according to chemical and electrical principles. Each parameter can be calculated, predicted, and managed. The movie may suggest sudden, unpredictable crises, but actual conditions follow measurable patterns. You observe that engineers use known formulas, such as the ideal gas law for oxygen and carbon dioxide calculations, to make adjustments that ensure continued habitability. The lunar module's role as a lifeboat is portrayed in both real records and dramatization. You note how the crew adapts power usage, oxygen distribution, and thermal control in a controlled, systematic manner. The cinematic version may heighten visual tension, showing cramped quarters or sudden alarms. Yet the real process relies on predictable calculations and engineering foresight. You see that the LM's performance was dictated by carefully managed physical principles rather than cinematic suspense. You examine the portrayal of re-entry in film. You notice that the capsule's deceleration, heat generation, and parachute deployment are simplified for dramatic effect. In reality, each factor is calculated with exact physics, including Newtonian mechanics, thermodynamics, and fluid dynamics. You follow how expected forces, temperatures, and velocities were precisely monitored. The cinematic depiction may amplify risk or show rapid sequences of events, but real outcomes are predictable and supported by rigorous measurement. Human physiology is another area of distinction. Movies often show exaggerated reactions to G-forces, oxygen deprivation, or stress. You track medical data showing heart rates, oxygen saturation, and muscle response that correspond closely to predicted physiological behavior under acceleration and microgravity. You notice that the crew's ability to remain functional reflects known limitations of human biology, integrated with life support systems designed according to predictable scientific parameters. You notice how the timeline of problem solving is altered in films. Decisions that in reality took hours or involved multiple iterative calculations may be shown as instant solutions. You follow real mission transcripts where procedures are repeated, verified, and sometimes rehearsed using simulations on Earth. Each adjustment is grounded in physics and engineering, reflecting the predictable consequences of actions rather than narrative expedience. You observe the portrayal of teamwork. While films emphasize dramatic tension between characters, actual mission success relied on systematic collaboration guided by known protocols. Roles are clearly defined, responsibilities shared, and verification occurs at multiple levels. You see that the predictable application of expertise, rather than emotional improvisation, ensures that every procedure maintains safety and efficiency. Telemetry, checklists, and communication form a structured framework for decision-making. Technical problem-solving is illustrated through both real and dramatized accounts. You note examples such as jury-rigging CO2 scrubbers, where the real solution involved calculating flow, chemical reaction rates, and material compatibility. In films, the focus may be on the visual or emotional impact of the action. You follow how the underlying success is determined by precise calculations, knowledge of chemical reactions, and engineering reasoning, showing that science governed outcomes rather than cinematic tension. You examine the depiction of suspense during emergencies. Movies may heighten alarms or present exaggerated visual hazards, but in reality, every anomaly was quantified and managed according to predictable physical principles. You notice that risk assessment, redundancy, and prior training provide a framework that makes outcomes manageable. Each solution relies on measurable variables and verifiable calculations, reinforcing the predictable and reproducible nature of applied science in spaceflight. You reflect on the broader implications of comparing real events with cinematic portrayal. You observe that while storytelling simplifies and dramatizes, the true mission demonstrates the consistent reliability of engineering, physics, and human skill. Measurements, telemetry, and procedural adherence illustrate that survival depended on predictable and controllable factors. You see that understanding the real sequence of events strengthens appreciation for both the precision of science and the craft of narrative storytelling. You notice the meticulous design of spacecraft systems, observing how every component includes redundancies. Life support systems, electrical circuits, and navigation instruments are duplicated or backed by alternative methods, ensuring continued functionality even if a primary system fails. You follow the predictable reasoning behind these design choices. By anticipating potential failures and calculating their effects, engineers minimize risk. Each redundancy reflects the systematic application of physics, engineering, and probability theory. You examine the importance of risk assessment. Engineers calculate potential failure modes for oxygen tanks, propulsion systems, and structural components. You follow these calculations, noting how expected probabilities, system tolerances, and human responses are combined into operational planning. The process is grounded entirely in mathematics and physical principles. You see that by quantifying risk in advance, spaceflight teams are able to make informed decisions during emergencies, balancing safety with mission objectives. Problem-solving becomes a central focus. You observe how the crew and ground teams work through unexpected situations systematically. You notice how they identify constraints, measure current conditions, and apply scientific laws to determine safe courses of action. Electrical limitations, oxygen levels, and thermal control are all managed with predictable calculations. Each decision arises from observation, measurement, and reasoning rather than guesswork, illustrating the practical application of physics and engineering under pressure. Redundancy in life support systems demonstrates applied chemistry and physics. You follow how oxygen generation, carbon dioxide scrubbing, and temperature control can be rerouted or repurposed. Calculations of gas flow, chemical absorption, and heat exchange are verified at every step. You notice how the crew uses these principles to extend the usable life of the lunar module systems, creating a controlled environment that sustains life under resource constraints. Predictable physical and chemical reactions provide a reliable foundation for improvisation. Engineering judgment is evident in every adjustment. You see how calculations of mass, thrust, and trajectory inform every maneuver. Even minor corrections are guided by Newton's laws and orbital mechanics. You follow the crew's methodical application of formulas, using onboard instruments and ground-based calculations to ensure accuracy. Predictable responses of spacecraft systems to input commands provide a framework within which safe adjustments can be made. You notice how simulations prepared the crew and ground teams for real emergencies. Practicing procedures in advance allows for predictable outcomes during unexpected situations. You follow how rehearsed responses reduce decision-making time and improve accuracy. Simulations replicate physical principles, environmental conditions, and mechanical behavior, allowing theoretical knowledge to be applied reliably in practice. This preparation illustrates the integration of learning, prediction, and observation in applied science. Communication plays a critical role in applying lessons. You observe how precise transmission of data between the crew and mission control ensures that calculations are verified and actions confirmed. Measurements of oxygen, electrical load, and navigation are cross-checked, and every decision is documented and reviewed. You notice that the predictable nature of physical systems allows both parties to anticipate consequences and plan responses, demonstrating the combination of observation, reasoning, and communication in applied science. You examine the psychological and physiological aspects of decision-making. Stress, fatigue, and microgravity all affect cognitive and physical performance. You notice how predictable human limitations are taken into account when planning shifts, monitoring vitals, and assigning tasks. Even the simplest action is guided by knowledge of reaction times, energy expenditure, and sensory perception, showing that applied science includes the interaction between human biology and environmental physics. Thermal control lessons emerge as you observe energy management. Heat generated by equipment and human activity must be dissipated efficiently to prevent system overload. You follow calculations of energy input, conductive and convective transfer, and heat rejection to radiators or storage. Predictable energy flow and thermal capacity ensure that internal temperatures remain within safe limits. The balance between power use and cooling illustrates the integration of physics, engineering, and environmental control. Redesign and post-mission analysis show how lessons extend beyond the immediate crisis. You notice how engineers review telemetry, sensor data, and crew reports to improve future spacecraft. Modifications to oxygen tanks, power distribution, and communication systems are informed by calculations and real-world observations. You follow the iterative process of design, testing, and verification, demonstrating the predictable, evidence-based evolution of technology rooted in applied science. You reflect on the role of teamwork. Each individual, crew member, engineer, or mission controller contributes expertise. Communication, verification, and structured procedures allow predictable, coordinated action. You notice how understanding of physical laws, system behavior, and human limitations is distributed across the team, enabling complex operations to succeed under constrained conditions. Collaboration becomes a practical demonstration of science in action. Problem-solving under resource constraints illustrates conservation principles. You observe how electrical load, oxygen consumption, and water usage are balanced to maintain equilibrium. Calculations of mass, energy, and chemical interactions allow the crew to ration supplies while preserving safety. You notice that predictable physical and chemical laws make such rationing not a guesswork exercise but a reproducible application of science. You notice the value of preparation and training. Repeated practice of emergency procedures allows predictable responses under stress. You follow how simulations replicate orbital mechanics, power limitations, and life support constraints, reinforcing the crew's ability to act according to principles rather than improvisation. Each rehearsal demonstrates how observation, measurement, and calculation can anticipate real-world challenges. You reflect on the integration of scientific knowledge. Newtonian mechanics, thermodynamics, chemistry, biology, and human factors are all applied together. You observe how predictable outcomes arise from accurate measurement, calculation, and controlled experimentation. The Apollo 13 mission demonstrates that survival is not accidental. It depends on precise understanding and deliberate application of natural laws. You see that every successful adjustment, calculation, and procedure is grounded in verifiable science. You notice how curiosity and learning are sustained through observation. Each anomaly, constraint, or challenge provides data that informs future missions. You follow how telemetry, chemical analysis, and engineering review create a feedback loop of knowledge accumulation. Scientific principles applied methodically continue to guide design, procedures, and training long after the mission concludes. You sense that these lessons extend beyond spaceflight. Risk assessment, redundancy, measurement, and verification are principles that can be applied in many technical and scientific endeavors. You observe how predictable laws of physics and chemistry form a foundation for decision-making under uncertainty. Even in high-stress, high-risk situations, structured reasoning and adherence to known principles allow safety and success. You observe how Apollo 13 became a benchmark for spacecraft design and operational safety. Engineers studied every telemetry reading, oxygen measurement, and electrical fluctuation to refine future spacecraft. You notice how the mission emphasized the importance of redundant systems, careful monitoring, and the predictable behavior of mechanical, electrical, and chemical processes. Each observation contributed to the knowledge base that guides modern spacecraft engineering, demonstrating that lessons from precise measurement and analysis create long-term improvement. Procedural revisions were made following the mission. You follow how checklists, emergency protocols, and simulation routines were updated to account for the anomalies experienced. Each procedure reflects predictable behavior based on physical laws and engineering principles. You notice how careful documentation ensures that future crews can respond effectively to similar conditions, translating past challenges into actionable, science-based preparation. Materials science saw rapid development as a result. Heat shields, wiring insulation, and pressure vessels were re-evaluated using data from Apollo 13. You track how engineers tested material response to thermal loads, chemical exposure, and mechanical stress. Predictable properties such as thermal conductivity, tensile strength, and oxidation rates guided improvements. These analyses ensure that future spacecraft can better withstand extreme environments, grounded in rigorous application of physics and chemistry. Human factors also evolved. You observe how crew selection, training, and monitoring now integrate lessons from physiological response under stress. Heart rate, oxygen consumption, muscle fatigue, and cognitive function are carefully measured and incorporated into design decisions. You notice that predictable human responses inform life support requirements, work schedules, and emergency procedures, demonstrating the seamless integration of biology and engineering. Telemetry and data collection techniques improved substantially. You follow how sensors were refined, redundancy increased, and measurement intervals optimized. Real-time monitoring became more precise, allowing engineers to anticipate issues before they escalate. Each system relies on predictable physical and electrical principles, ensuring that observations are accurate, actionable, and reproducible. You notice the emphasis on simulations and predictive modeling. Engineers now employ advanced computational methods to anticipate spacecraft behavior in a wide range of scenarios. Forces, pressures, chemical reactions, and thermal loads are calculated under controlled assumptions. These simulations rely on the same principles observed in Apollo 13, demonstrating that real-world data can improve predictions and prevent failures by applying physics and mathematics systematically. Training protocols incorporate unexpected contingencies. You observe how astronauts practice rerouting power, adjusting life support systems, and compensating for system failures. Each scenario reflects an anticipated, predictable response of spacecraft systems under constrained conditions. By integrating these lessons into training, future crews are able to rely on known physical and chemical principles to maintain safety, ensuring that preparation, not improvisation, guides survival. You follow the development of risk management practices. Engineers analyze failure probabilities, simulate system responses, and implement redundancies based on predictable outcomes. You notice how contingency planning is rooted in measurement, calculation, and modeling. Even the most unlikely scenarios are considered scientifically, creating a framework where risk is quantified, controlled, and mitigated using established laws of nature. Space agencies expanded interdisciplinary collaboration. You observe how physics, chemistry, engineering, biology, and materials science are combined in spacecraft design, operations, and problem-solving. Each discipline contributes predictable, measurable insight. You notice that the Apollo 13 mission highlighted the necessity of integrated scientific knowledge, showing that successful exploration depends on harmonizing multiple fields with precision and rigor. You see how data from Apollo 13 informs spacecraft redundancy. Systems are designed so that failures in one component can be compensated by another, following calculated tolerances. Electrical circuits, fuel lines, and life support systems are interconnected in ways that reflect precise understanding of energy transfer, fluid dynamics, and chemical reactions. Predictable system behavior allows engineers to design contingencies that protect both crew and mission objectives. You track the role of documentation and scientific reporting. Engineers, scientists, and astronauts publish detailed findings, ensuring that lessons were accessible to future missions. You notice that data collection, analysis, and presentation rely on rigorous methodology. Physical measurements, chemical analyses, and mechanical assessments form a reproducible record that extends knowledge and informs ongoing exploration. Accuracy and precision are paramount, reflecting the predictable nature of scientific inquiry. Safety culture was strengthened globally. You observe how operational protocols, emergency drills, and verification procedures are now standard practice. Each process is guided by predictable physical laws, measurable environmental conditions, and validated human factors research. You notice that survival in space is dependent on preparation grounded in science rather than chance, illustrating how Apollo 13 set a precedent for structured safety measures. Engineering education also adapted. You see how case studies from Apollo 13 are used to teach problem-solving under constrained conditions. Students learn to calculate forces, energy usage, and system tolerances, applying physics and chemistry to practical scenarios. Predictable behavior of materials and systems becomes a foundation for understanding complex interactions, reinforcing that careful reasoning, calculation, and observation guide safe spacecraft operation. You observe the influence on public understanding of science. Telemetry, technical briefings, and mission reports allowed wider audiences to appreciate the predictable laws that governed life in space. You notice that knowledge of physics, chemistry, and engineering provides clarity about how survival was possible. Real-world data demystifies high-risk operations, showing that structured scientific knowledge, rather than luck, determines outcomes. You follow the long-term technological evolution. Components such as oxygen regulators, power systems, and navigational instruments were redesigned based on lessons from Apollo 13. You notice how predictable physical laws, material behavior, and chemical reactions guide iterative improvements. The spacecraft of the future reflects an accumulation of scientific knowledge, practical testing, and careful measurement, creating more reliable, safer exploration platforms. Research and development continue to be informed by this mission. You see experiments that test structural materials, energy systems, and life support efficiency. Each investigation applies physics, chemistry, and biology in measurable ways. You notice that predictive modeling, informed by empirical observation, ensures that knowledge gained from Apollo 13 enhances subsequent missions in a consistent, scientific manner. You feel the mission's legacy in modern crewed and robotic spaceflight. Procedures, safety measures, and design principles trace directly to the lessons learned from the challenges faced. You notice how engineering, physics, chemistry, and biology converge to ensure that spacecraft perform predictably under extreme conditions. The mission stands as a reminder that deliberate observation, measurement, and application of scientific principles safeguard life in environments beyond Earth.